This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 3, Helical Compression Springs. Vessels and cylinders held pressure. A spring stores it. Picture a straight torsion bar wound into a coil. When you push on the coil, every bit of wire twists, so the wire carries shear. 3 relations run every spring problem: the rate that sets how stiff it is, the corrected shear stress that decides if it survives, and the energy it banks. We build all 3, then work a full example. Concept 1. The coiled torsion bar. Because the wire twists, the stress is shear, and the handbook gives it as Ks times 8fd over pi d cubed. The 8fd over pi d cubed piece is the plain torsional shear. Ks corrects for the extra stress on the inner fiber, where the coil curves tightest. Everything hangs on one ratio, the spring index C, mean diameter over wire diameter. A tight coil small c means a bigger correction. Use the printed factor exactly. Concept 2. The spring rate. Stiffness is d to the 4th times g over 8 times d cubed times n, and force is just k times deflection. The headline is the 4th power on the wire diameter. It swamps everything else, so a slightly thicker wire is dramatically stiffer, while adding coils or opening up the coil diameter softens the spring. This same rate reappears in Lesson 5 as the helical entry in the equivalent stiffness table, a spring driving a vibrating mass. Concept 3. Stored energy. A linear spring's force builds straight with deflection, so the work you feed in is the triangle under the force deflection line, 1/2 kx squared, or equally 1/2 fx. Shift from one deflection to another, and the change is k times the difference of the squares over 2. Energy scales with the square of deflection, which is exactly why a spring is a compact place to bank mechanical energy. Concept 4. How strong is the wire? Spring wire is stronger the thinner it is, so tensile strength is a power law, A over d to the m, with A and m read from a material table by wire type. Music wire, oil-tempered, hard-drawn. Match the units. The kpsi column goes with the wire diameter in inches. This gives you the tensile strength. Lesson 4 converts it into the allowable shear stress you compare the calculated stress against. Setup. A steel helical spring, 10th-inch wire, 8 10th-inch mean coil, 10 active coils, and a 20-pound load. Shear modulus is the standard steel value. We want the whole picture: index, rate, deflection, corrected shear stress, and stored energy. The plan runs left to right. Index first, because it drives both the rate correction and the stress. Then rate, deflection, stress, and energy. Solve. Part 1. Index is diameter over diameter, a clean 8. The rate is d to the 4th times g over 8d cubed n. Plug in, and it's about 28 pounds per inch. Deflection is just load over rate, a bit over 7/10 of an inch. Carry the unrounded rate forward, so the stress and energy match. Solve. Part 2. The correction factor at index 8 is 34 over 29, about 1.17. The raw torsional shear, 8fd over pi d cubed, is around 40,700, and the correction lifts it about 17% to roughly 47,800 at the inner fiber. Reach for the printed factor, not a memorized Wahl form. Solve. Part 3. Stored energy is 1/2 kx squared, about 7.1 inch-pounds. Check it the other way, 1/2 fx, and it lands on the same number. When the two routes agree, your rate and deflection are consistent. A free error check every time. Traps. 5 ways this bites. 1. The spring index is mean over wire, and you need it first. 2. The rate is wire diameter to the 4th on top, coil diameter cubed on the bottom. Don't swap the powers. 3. N is active coils, not total. 4. Use the printed correction factor, not a memorized Wahl form. 5. Pi d cubed sits in the denominator of the stress, and energy scales with the square of deflection. And keep G for compression. Torsion springs bend, and switch to E next lesson. Quick recall. Everything starts from the spring index, mean over wire. It sets the correction factor and the rate. The rate gives you deflection. The corrected shear stress tells you if the wire survives. 1/2 kx squared is the energy banked. Wire strength is a size-dependent lookup, and the same rate returns next week as the helical equivalent stiffness. Golden rule: get the index first, and the rest falls out. Next up, Lesson 4. Springs 2. This spring twisted its wire and stored energy in shear. Next, we flip the loading. A torsion spring bends its wire, so the elastic modulus E takes over from G, with its own correction factor. We add the end condition dimension table, combine springs in series and parallel, and treat a cyclically loaded spring as a fatigue problem. Everything's at peprepengine.com. Cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.